Hello and welcome to my talk. My name is Justin Tamasipur and I will be presenting the paper on the wind tunnel measurements of non-dimensional lift coefficient of a boomerang and comparison to theory. The agenda of this talk is as follows. I will provide a brief introduction to boomerangs involving the history of boomerangs and boomerang competitions. This will be followed by an overview of prior work on the aerodynamics of boomerangs. We will then describe the wind tunnel in which the lift measurements were taken, and then compare these results to the theoretical predictions of prior work. We will end the talk with a summary and conclusions of our work. Let us start with a brief history of boomerangs. There are two types of boomerangs, non-returning boomerangs and returning boomerangs. Non-returning boomerangs were found in all continents and many countries, ranging from Egypt, Europe, India, and Australia. Non-returning boomerangs were primarily used for hunting. Returning boomerangs, on the other hand, were only found in Australia. They were primarily used as toys. There are a wide variety of competition events. At each competition event, a specific type of boomerang is used to achieve the maximum score. For example, a traditional V is used in the Aussie round, while a three-blader is the most common type of boomerang used in fast catch. Other examples are the hook that is commonly used in long-distance competitions, while odd-looking boomerangs such as the Space Ranger are used in the MTA event. I will now provide a quick overview of recent prior work on the aerodynamics of boomerangs. In the 1970s, Felix Hess did an extensive study on the aerodynamics of boomerangs and developed the equations to numerically solve for the flight characteristics of boomerangs. He collected experimental data of the lift generated by a boomerang immersed in water with various rotational and translational speeds. In 2012, John Vosburgh took a significant step forward to enhance our understanding of the aerodynamics of boomerangs by applying blade element theory to derive analytical expressions for the time average lift and rolling moment. In 2019, Prasad Gautam extended Vosburgh's work to include the effect of reversal of airflow and reversal of angle of attack as the boomerang blades rotate. In Hess's work, the non-dimensional lift coefficient is proportional to the non-dimensional rotational speed squared, chi, which is given by r omega over v, where r is the blade radius, or blade length, omega is the rotational speed, and v is the translational speed, or wind speed. Under the typical operating conditions for boomerangs, which is when chi is between 0 and 1, Vosburgh predicts the non-dimensional lift coefficient is quadratic with respect to chi plus a constant. Under the same operating condition, Gautam predicts that the non-dimensional lift coefficient is linear in chi plus a constant. A compact wind tunnel of length 7 meters was used to find the lift force produced by the rotating boomerang at different incidence angles to the airstream. The wind tunnel was especially constructed to allow a spinning boomerang to be suspended in the middle of a test section. The boomerang is attached to a 6 millimeter diameter steel spindle passing out of the tunnel through a small hole and is driven by a 12-volt variable speed motor that can rotate up to 28 rotations per second. The wind speed in the tunnel is also variable with a maximum of 14 meters per second. The lift forces are measured by a load cell holding the suspension beam above the center of the boomerang. Additionally, 3 water tanks and floats help to balance the weight of the motor and have the added benefit of vibration damping and reducing the load on the suspension beam. Anchor screws and wires are used for resisting drag forces produced in the X direction. The boomerang used in this paper is the variable inclination pitch angle ring, VIPAR, and has 4 blades with an average blade pitch of 5.5 degrees, top-down symmetric airfoils, a 30 millimeter cord, a maximum thickness of 5 millimeters, and a blade radius of 13 centimeters. The VIPAR is mounted to a spindle that can change the angle of incidence to the wind. For each angle of incidence, the lift was measured for various wind speeds and rotational speeds. The constants in the previous expressions were found by analyzing various aspects of the wind tunnel data. The ratio between the lift coefficient over the trailing edge and leading edge was found to be 3/4 by taking the ratio between the lift generated by spinning the boomerang in the positive and negative directions. The lift coefficient over the leading edge was found by comparing the behavior of the measured non-dimensional lift coefficient at chi equals 0 against various angles of incidence to Gautam's prediction, which correctly predicts that the curve is linear with the given slope. The constant h in Hess's prediction was found by creating a best fit curve while maintaining a realistic slope. We will first consider the measurements collected for an angle of incidence of 1.2 degrees. This graph shows the lift generated by the boomerang for constant translational speeds as a function of the rotational speed. It is important to note how high wind speeds give chi values within the typical operating condition of 0 and 1. Smaller translational velocities will give chi values greater than 1, and so these trends are not of interest. For high translational speeds, the lift is linear in the rotational speed, and so we expect the non-dimensional lift coefficient to be linear in chi. The graph of the non-dimensional lift coefficient precisely indicates this. The trend seems to follow Gudim's linear prediction quite well. Vastberg's trend overpredicts the y-intercept, and Hess's quadratic prediction does not match the data. Next, we consider the measurements taken for an angle of incidence of 5.2 degrees. We see the same linearity in the rotational speed for high translational speeds as the previous graph. Therefore, we expect the non-dimensional lift coefficient to be linear in chi once again. This seems to be the case, and the trend approximately follows Gudim's linear prediction. For high chi, there is some deviation in measurements towards Vastberg's trend. For small chi, however, Vastberg overpredicts the y-intercept. Hess underpredicts the y-intercept, and the quadratic trend does not provide a good fit for the measurements. Finally, we consider the measurements taken for an angle of incidence of 10.5 degrees. The lift is again linear in the rotational speed, and so we expect the non-dimensional lift coefficient to also be linear in chi. This is the case once again, and the measurements match Gudim's linear prediction well. The quadratic trends of Vastberg and Hess do not provide a good fit for the measurements. In summary, a wind tunnel was constructed to measure the lift of a boomerang at various rotational speeds, translational speeds, and angles of incidence. Theoretical predictions of the non-dimensional lift coefficient of Hess, Vastberg, and Gudim were compared to these measurements. The measurements show that the non-dimensional lift coefficient is linearly proportional to the non-dimensional rotational speed in the useful region of the non-dimensional rotational speed, which is when it is between 0 and 1. The measurements approximately agree with Gudim's predictions of the non-dimensional lift coefficient being linearly proportional to the non-dimensional rotational speed. Therefore, considering the reversal of airflow and reversal of angle of attack, as Gudim has, is necessary to accurately model the lift in boomerangs. This is a picture of my research advisor Prasad Gudim showcasing his array of boomerangs. Thank you for attending this talk.